Hello, today I want to take you through a real simple example of stoichiometry to sort of highlight what stoichiometry is and why we need to use it. So in this example, we have how much water can you make from 100 grams of hydrogen gas when reacted with oxygen from the air? And a second part of this question is then how much oxygen gas did we need to use from the air? So the first thing we need to do for any stoichiometry is write out the chemical equation. Plus O2 makes H2O. So remember that both hydrogen and oxygen gases are diatomic, so we have H2 and O2, and they make water H2O. Now, if I draw that, I'm going to use blue here for hydrogen. There's an H2, and I'll use, say, green for oxygen. What they'll make then is an O with two H's, a little sort of sideways Mickey Mouse there. And so that's what the visual representation of this equation is. But if you look carefully, then it looks like one of our oxygens here is missing. And so this is an unbalanced chemical equation. So that's the next step you have to do always with stoichiometry, is to balance. And so I see I have two hydrogens on both sides. I have two oxygens on my reactant side and one oxygen on my product side. So I'll put a 2 here. That makes my oxygens balanced. And now I have four hydrogens on the product side. And so if I put a 2 here, I now have a balanced chemical equation. But what that means is, for my picture, is I need to draw two H2s and two H2Os get made. And so this is basically the minimum amount of actual hydrogen molecules and oxygen molecules you need to make a minimum amount of water, which is 2 and 1 and 2 that make 2. And so that's the idea behind the balanced equation. But what that really means, though, is the 2 and the 1 and the 2 aren't super important, other than that it's a ratio. Hopefully you can see here that if I doubled my hydrogens to 4, let's say, I would need to also double my oxygens to 2, and I could make 4 waters. And so it's the ratio that's important here. So where does stoichiometry come in here? Well, stoichiometry is about predicting how much of a product you'll make or how much of another reactant you need in order to make things go together properly. So if I only had two actual hydrogen gas molecules here, and I can see that I can only make two water molecules with that. And so if I wanted to know the mass of the water, which is usually what we're trying to find in stoichiometry, I could add up the mass of two oxygens, which is 32 AMUs plus 4 hydrogens, which is another 4.04 AMUs. So we would know then that we have a total of about 36.04 AMU. But we don't usually deal in that, right? We're dealing with much, much, much larger numbers of actual molecules so that we get into looking at things in grams. But the ratio here is what's important. So if we look at those, we can see here that the hydrogen to water ratio is a 2-to-2 ratio. You need two of those and you'll make two, which is really, if we reduce that, just a 1-to-1 ratio, which is great. It doesn't matter then if I had, say, 15, I would make 15 waters. If I had 3 dozen, I would make 3 dozen waters. If I had 6.2 moles, that's a number, it's a counting number, I would have 6.2 moles of water, so on and so forth. And so the same is true with the other participants in this reaction too. There's also a ratio of the hydrogen to oxygen. Here, that's a 2-to-1 ratio. And so that's reduced. But what that means is for every 2 hydrogens I have, I need 1 oxygen to make this reaction work. So if I had, say, 6 hydrogen gases, then I would need 3 oxygens. If I had 50, I would need 25. If I had 8.4 moles, then I would need 4.2 moles of that, so on and so forth. We can do the same thing with the oxygen and the water too. If we happen to know something about it, in this question we don't, we know something about the hydrogen, but imagine the question was worded differently. Well, we'd have to look at that ratio, which is a 1-to-2 ratio. So again, that means if you have 3 dozen oxygen molecules, then you will make 6 dozen waters. If you have 2.7 moles of oxygen, you will make 5.4 moles of water, so on and so forth, so on and so forth. So that's the idea behind the mole ratios, and it's going to be really important for solving stoichiometric problems. That's the idea here. So if I wanted to answer this question, I need to figure out a few things. And so the first thing I need to know is what does the question give me here? So let's start with that. I'm going to rewrite this here. 2H2s, and I know my mass here is 100 grams. Plus O2, make 2H2Os. This, I don't know the mass of, but that's the question I've been asked. How much water or oxygen are we going to use from the air? And the first question is, how much water are we going to make? And so this ratio and the diagram above them are going to help us, these ratios. So first thing I need to do is convert the mass to a number. I need to know how many. I don't really care how much they weigh, because oxygens and hydrogens weigh different amounts. It's like bowling balls and feathers and things like that. We need to know the number that go together. And for that, we need to know the moles here. And so to find the moles, this is the only one I can do since I only know its mass. I will use little m over big M, which is 100 grams divided by 2.02. We get that off the periodic table. Hydrogen is 1.01, and so there's 2 of them in there. Note, I am not using the coefficient in front. I'm just using the molecule itself for this. The ratio will come in later. Those coefficients in front will come in later. And so when I divide those two, I get 49.50 moles. So now I know how many moles of hydrogen I have, or I've answered the question, how many do I have? And so the next question then is, how do I use that to figure out how much water I'm going to make? Well, I go back to my ratios here. If I know that this is a 1-to-1 ratio, then if I have not 1, but 49.5 moles of this, well, what is this number that's going to go on the other side? 1 is to 1, as 49.50 is to 49.50 moles. So now I know that number. And that's the real trick to stoichiometry there, is to use that ratio to help us figure some things out. Now, sorry, that's not mass. 49.5 moles here. So how do I figure out the mass? Well, I go back to little m is n times big M, and I know I have 49.5 moles of that water. You can see that clearly in the diagram, that those go 1-to-1. So if it's 49.5 of one, you have 49.5 of the other when it comes to the hydrogen in the water. And I need to look this up on the periodic table. 2 hydrogens and an oxygen. Again, we are not using the coefficient in front. I'm using just the molecule itself for this. And I get 18.02 grams per mole. Multiply those two things together, and I get 892 grams of water. So I've answered the first question here. Now you might be saying to yourself, whoa, why, how are we getting 892 grams out of this? We only started with 100 grams of hydrogen. That's maybe a magic trick, but it's not, because we've only looked at the hydrogen in this to make the water. There is another part called oxygen, and so if we wanted to know how much oxygen have we used from the air to make this reaction run? Well, you might be able to look at this because the numbers are relatively easy and say to yourself, I'm going to bet that it's actually 792 grams of oxygen, since if I put those together, hydrogen and oxygen, that would add up to 892 grams. So that's a good bet. I'm going to go take that bet, but let's do it formally so that in case the numbers aren't so easy to kind of inspect, we'll have an idea how to do this. And we're going to do it the exact same way, even though oxygen is on the reactant side and so is hydrogen. It doesn't matter. These things, all you need to know is the mass of one of any of the chemicals in a chemical reaction, and with the balanced equation, then figure out anything else. And so in this case, I want to check out hydrogen with oxygen. I know that's a 2-to-1 ratio this time. Now, the beauty here is I've already worked out what 100 grams of hydrogen is. I already know it's 49.5 moles. And so if I want to know what the oxygen is, well, 2 is to 1 as 49.5 is to this x, this unknown here. And so by the ratio, it's going to be half. Now, sometimes it's not, again, as simple as just a half. And so the trick that I like to do here is called the crisscross method. I write this out the way I have, where I write my elements, then I write the ratio from the balanced equation, and then I write whatever one that I know here. In this case, it's the hydrogen. I usually write it first, the one I know, but you don't have to, as long as you have the right number with the right element and the right unknown here with the unknown element. And so what you do then is just cross multiply this. 2 times x is 2x. 1 times 49.5 is 49.5. And when I divide out 2 on both sides, I get x equals 24.75 moles. And so now I know my moles, or how many, it satisfies that ratio of oxygen I have. And now let's double check this. We've already guessed that it's going to be 792 grams, but let's just work that out for oxygen. Mass will be little n times big M. In this case, 24.75 moles times, what's the molar mass of oxygen? Well, 2 oxygens off the periodic table give me 32 grams per mole. No, my moles cancel here in this. And I get an answer of, we guessed it, 792 grams. And so that's how you do stoichiometry. That's what stoichiometry means. It means looking at how many we're starting with here, and then how many can we possibly make. You can look at this picture and you can see that we couldn't possibly have made, say, 10 waters out of that. There's just not enough hydrogen and not enough oxygen. And so knowing how many we can make by looking at the balanced equation and getting that ratio, then using the well-known equation in its various forms, little n over big M, and then backwards to get mass back out. There we have all we need to solve for any of the reactants or the products in a chemical equation.